Kia ora and welcome to video 14 in the series Delightful Differentiation. Apologies for the slow upload on this video. Been feeling a little bit under the weather today and the Black Caps got knocked out of the World Cup, so I'm not very happy about that either. The video is going to be presented by a former student of mine, Lam. He was an incredibly bright student, pretty much in everything that he did, but also a very, very humble young man. Thank you so much, Lam, for putting this video together in the middle of your busy exam season at university. Not only did he present a really clear solution to the problem, but I went back to him and said whether he'd considered it a different way. He's kindly offered to record a second video so that we've got two solutions to this problem. Here is the question. We're finding the value of this limit if it exists. If you've never seen limits before, the notation there, the limit is h approaches 0, means that you need to consider h when it's really, really small. So approaching 0 on a graph means approaching from both sides. You need to consider what's happening when h is like 0.0001, very close to 0 but positive, and you also need to consider what happens when h approaches 0 from the negative side. Okay, so give this a go. Enjoy the two solutions that follow the intro music. They're pretty awesome.
The question today is to find the value of this limit if it exists. So before we tackle the problem, it's good to know what we actually know about limits in the first place. The first thing, which is quite well known, is that limit as x approaches 0 of sine x over x is 1. This is quite important in calculus, and so that's why the proof is left as an exercise for the readers. And secondly, judging from the question, it's good to know the limit as x approaches 0 of tan x over x. And through a bit of manipulation, you can show that this is the same as the limit as x approaches 0 of sine x over x cos x, which you can split into two different limits, where the second one is just 1. And therefore, our initial limit is 1. Through this information, we hopefully can try to simplify the problem so that we can turn the question into some form of limit as h approaches 0 of tan h over h. Now, looking at the question, there are two things we can tackle first, and those are the two tangents on the numerator. So another thing we know is that tan of a plus minus b equals tan a plus minus tan b, and then over 1 minus plus tan a tan b. So we can apply the formula to the first one, and it turns out to be equal to square root of 3 plus tan 5h over 1 minus square root of 3 tan 5h. And for the second one, similarly, we get square root of 3 minus tan 4h over 1 plus square root of 3 tan 4h. And then we can plug these into the limit, but then we would want to reduce the fractions to have the same denominator. And then just step by step, you have to expand everything out, but just do be careful with the signs. Afterwards, we can see that we can cancel some things out. For example, the square root of 3, the square root of 3 tan 5h, tan 4h. On the other hand, we have 3 tan 4h and tan 4h, and likewise tan 5h and 3 tan 5h, which we can add them up together. But if you notice, the entire big bracket just equals 1, because as h approaches 0, tan 4h approaches 0, and likewise tan 5h approaches 0, so we will only have 1 left. So now we get limit as h approaches 0 of 4 tan 4h plus 4 tan 5h over 3h. We can basically split this into two different limits, and you can tell that it's very close, very, very close to the form that we want. Given that there's a 4h and the 5h inside the tangent, we can try to change the denominator so that it also has a 4h and a 5h. And then we bring all the numbers outside, but there is still one problem left, and that is, while the tangent has 4h and the 5h inside, we still have the limit as h approaches 0. But this is a simple fix because we can say that as h approaches 0, this is equivalent to 4h approaches 0 and 5h approaches 0. So finally, we can apply the formula, and the entire limit is just 1 for either cases. So our initial limit is equal to 16 over 3 times 1 plus 20 over 3 times 1, which is 36 over 3, which is equal to 12. This question also has a second method, which is quite faster, and that is to use derivative by definition. So by definition, if we have a function f of x, then its derivative, f prime of x, is equal to limit as h approaches 0 of f of x plus h minus fx, and then over h. We could minus tan pi over 3, and then also plus tan pi over 3. So we can basically split this into two different limits, where each one is quite similar to the form that we want. Is that for the denominator of each one, we want 5h instead of 3h, and then for the other one, we want minus 4h instead of 3h. We can let u equal to 5h and v equal to minus 4h, and then plugging them into the limits, what we can see is that each of the limit is in the exact form of the derivative of tangent of x. So, therefore, by definition of derivative, this is equal to 5 over 3 times the derivative of tan of x at x equals to pi over 3 plus 4 over 3 times the derivative of tan of x at x equals pi over 3. Simplifying this is the same as 3 times derivative of tan of x at x equals to pi over 3, which is the same as 3 secant squared pi over 3, which equals to 3 times 2 squared, which equals to 12.